Hey everyone, how's it going today? We're gonna solve a few calculus problems. I'm reviewing some of my calc, and I thought, you know what? Oops, let me undo something. Would be nice to do this live. I don't know if the stream's running well though. Let me know if you're just coming in and you're having issues with the stream. So I'm reviewing problems for myself because it's been a little while since I've gone over this material. But if you have any questions, or if you'd just like to hang out for the time that I'm reviewing, that's perfectly fine. But today I'm going to go ahead and start with some related rates problems. Okay, so here's a problem. Here is a problem. We have a volume of a cube. Wait, no. Sorry, not that one. We have a paper cup, the shape of a cone, with a height of 10 centimeters and a radius of 3 centimeters. Okay, so we have this sort of paper cup, and the height is 10 centimeters. Height is 10 centimeters, and the radius is 3 centimeters at the top. 3 cm. Okay, and we're pouring water out of all things into this. Who would have known? Pour some water in there. That's a water drop. At a rate of 2 cubic centimeter per second. 2 cm cubed per second. And the question is, how fast is the water level rising when the water is 5 centimeters deep? So the water level is going to get to this point right here. Interesting problem. So I guess the very first thing I can do to get started is I can go ahead and write the equation of a cone. It's a circular cone. And so the volume is going to be V. I'm going to start in green. V equals, is that 1/3? 1/3 pi r u squared h. Okay, and I want to know how fast the water level is rising when the water is 5 centimeters deep. So the question is, how fast is the height rising, I guess you could say. When 5 centimeter deep. So there's going to be a time dependent related rates problem. We're going to have to differentiate in respect to time rather than with respect to height or with the radius, because the thing that's changing here is the independent variable is time here. That's the one that we're kind of like we're pouring water at a rate of 2 centimeter cubed per second. So what we want to do is take the derivative of the original equation with respect to time. That's going to be dv dt equals to 1/3 pi. These are constants, but I am going to take the time derivative of the stuff that do change with time, which is going to be the radius and the height. So those two things are going to change. And I can go ahead and we're going to need to use a rule. That's going to be the, whoa, that's a weird 3. It's going to be the product rule. So we're going to take the derivative of the first term times the second plus the derivative of the second term times the first for the product rule. So that's going to be 2RH dr dt. Ooh, it's going to be interesting. Plus r squared dh dt. The radius is changing too with respect to time, surprisingly. But can I rewrite the radius in terms of something else? That way I don't have so many things in the way, because I now have a new unknown, which is dr dt. Maybe I could do this. So this is where where my experience is kind of wearing out a little bit. We might be able to draw a triangle here. And we know that the height is going to be this side of the triangle. This is always going to be the radius, and this hypotenuse is going to be the square root of r squared plus h squared. So I could probably write one in terms of the other. That way we don't have to worry about having two different things in here. Can we write one in terms of the other though? That'd be a good question. Should we? Because that might make things even harder. We gotta find out the rate at which the radius changes. Dr dt. Might need to think about this one a little bit more carefully. We can definitely find out this. We can find out r and h. We can find r squared. We're trying to find this. We have this as an unknown. Maybe we could use similar triangles? Maybe I can linearize the radius in terms of the height. Oh, that makes a lot of sense. Okay. Okay, so what we can do, we know that this angle here, okay, so this angle here, let's call it theta. We know that the tangent of theta is equal to opposite over adjacent, which is going to be 3 centimeters over 10. But that's going to be equal to r over h, which is going to be our variables. So I can rewrite this as 3 over 10. So that's going to be the case that r is equal to 3/10 h. So maybe I should rewrite everything over here in terms of h. That'd be way better. So I'm just going to go ahead and do that. So I'm going to go ahead and cross this part out. Move this down, and we're going to do dv dt is equal to 1/3 pi d dt of r squared. It's going to be now 3/10 h cube. So this looks a lot better now. Now I could go ahead and take a time derivative. So that's going to be equal to 1/3 pi. And it's going to be times 9/10 h squared dh dt. Much better. Okay. And now we just need to find h, because we know what the rate at which we're pouring water in. We want to find this, but we do need to solve for h. So what is the volume when the height is 5 centimeters? So volume, hang on, let me use a different color here. I'm going to use red. Volume equals to 1/3 pi 3/10 h cube. So when the height is 5 centimeters, 5 times 5 is 25, times 5 is 125. So that's going to be, let's go ahead and cancel the 3's there. 125 divided by 10 is 12.5 pi. That's the volume. 12.5 pi cubic centimeters. But I didn't need that. We don't need that. We just need to know, we already have h. I don't know why I did that. So we can just go ahead and plug in for the volume, the rate at which we're pouring water in, which is 2 centimeters cubed per second in purple, equal to 1/3 pi times 9/10 times 5 squared dh dt. And now it's just a simple calculator problem. Now we just gotta plug this in and solve for dh dt. So okay, so we're gonna have 2 equals 9 divided by 3 is 3, so we're gonna have 3/10 times 25 times pi dh dt. I'm going to go ahead and multiply by 10, divide by 3, well, divide by 75, because that's 75 there. So that's going to be 20 divided by 75. 75 pi, I'm dividing by pi too. That's equal to dh dt. And if we put this in our calculators, that's going to be 20 divided by 75 divided by pi. It's equal to 0.085 centimeter per second. Does that make sense? That makes sense. Can we use something? Can we use something that we learned, or about the volume of the cone? It is a variable rate, so it's not as easy as comparing with something else. But we do know that with a cone, being that the radius is a little thinner here, the height is going to change faster early on, and then it slows down in the top. The full volume of the cone is going to be 1/3 times pi times the radius squared, which is 9 times the height. The full volume is 94 divided by 2, so it's going to take 47 seconds to fully fill up. 47 seconds. So it's close to the center. So on average, I would expect it to be roughly about 0.085, maybe a little more, for the speed at which the height increases of that water level. So I'm just gonna go ahead and just assume that it's linear, which is not. But just for the sake of testing, that's gonna be 10 centimeters divided by 0.085, and yeah, bad. I got 117 seconds, which is not the best. But I'm fairly confident with this result, though. Very confident with. What we did was we went ahead and wrote the volume of the cone. We took the time derivative of both sides, but then we realized that we needed to actually change one of the variables as a function of the other. And we were able to do that using related angles here, related triangles. Because we can relate the 3 centimeters and the 10 centimeters with a variable r and h. We were able to rewrite that as r equals to 3/10 h. And plugging that back into the original equation. Hey, what's up, Bit? Hi, kitty cutie. Plugging that back into the original equation, we had everything in terms of h, which is great, because now you could just solve for your DHD. And yeah, and from there it's just crunching the numbers. Pythagorean, I didn't have to use it. I thought I might have to use it, but I didn't really need it. I just had to use related triangles because if you look at the cone, the cross section of the cone right down the center, we're trying to find how fast the water is filling as you fill it up. Once the water is about halfway up. You can kind of divide this as two separate triangles. So this could be one triangle, and this is the other triangle. And we're linking knowns with unknowns, so we already knew that this radius is 3 right here. And we also know that the height was 10. And we used the fact that these angles are shared to link a unknown radius r and unknown height h. It's pretty neat. It's a pretty fun problem. Definitely had me scratching my noggin for a second there. Are you done streaming, kitty cutie? Or are you still playing? Oh, by the way, I'm on YouTube too right now. We're on Twitch and YouTube, by the way. Whoever's watching. Oh, hang on. Let me give you the link to the YouTube. So we're taking a very tiny little break before we move on to another problem. I'll get you the link here in a second. Their problem. Okay, here we go. So very cool problem. Let me see if I can find another related rates problem here. So if you're just coming in, I'm just reviewing problems for myself. But if you're learning right now, or if you just want to hang out, if you're learning, that's great because we could learn together. Well, I could relearn, and you can kind of think through the thought processes. But if you just want to hang out, fine. Find a good related rates problem. You know, all these are very similar actually. Now that I'm looking through all these, they're all either triangles, they're cubes that are growing. Okay, here's one. Miyabi. What does that mean? What that be? Let me see if I can describe the problem well here. Awesome, but Chinese? Oh, really? You're learning Chinese? A television camera is positioned 400 feet from the base of a rocket launching pad. Okay. So we got 400 feet. We have a camera here. That's my camera. The angle of elevation. Okay, so there's a rocket launching pad right here. That's a rocket launching pad. Directly, it means Cal. What now? What? Okay, so the angle has to change. This angle that I'm pointing at. I'm just gonna call it theta. Has to change at the correct rate in order to keep the rocket in sight. Also, the mechanism for focusing the camera has to take into account the increasing distance from the camera to the rising rocket. So we're gonna go ahead and assume that we have a rocket here. And it has a speed at this point of 600 feet per second. When it has risen 3,000 feet. 3,000 feet. How fast is the distance from the television camera to the rocket changing at that moment? So there, it looks like it's a multi-stepped problem here. So let me write it out. How fast is distance d, I'm going to call it d, changing at that moment? So this distance d here, which I'm going to do in orange. I haven't used orange in a while. So I see a triangle. We could probably solve it using triangles. So let's go ahead and link the base, the height, and the distance between the rocket and the camera. And I actually missed out a 0 here. So that's going to be, of course, your x squared, your horizontal distance plus your vertical distance squared equals to d squared. We're going to go ahead and take a derivative with respect to time because we want to know how fast this is moving. So that's going to be 2x dx dt plus 2y dy dt equals 2d. Why do I always use d? dd dt. I'm going to go ahead and cancel the 2's. Just imagine we divided by 2 everything. And dx dt, that's going to be 0. And that's because our horizontal distance isn't changing. But dy dt, on the other hand, that is going to be 600. Because at that moment in time, the rocket is moving at 600 feet per second. And we also know the height is 3,000 feet. So that's 3,000 times 600. And that's equal to the distance d, which we don't have yet, times dd dt. And we're going to have to find that distance using, now we're going to use Pythagoras. It's going to be 4,000, 3,000, and if you remember from trig, this is a very popular triangle. It's the 3, 4, 5 triangle. So this is going to be 5,000 without needing to use Pythagoras. So that means this is going to be equal to 3,000 times 600. That's equal to 5,000. Oops. dt. And I'm just going to go ahead and plug in my calculator. 3,000 times 600 divided by 5,000. The distance between the camera and the rocket is changing by 360 feet per second. I love the background music. It's like elevator music, right? It's very nice to the ears. If the television camera is always kept aimed at the rocket, how fast is the camera's angle of elevation changing at that moment? So now we want to know, I'm going to now start using light blue, purple. Now we want to know what is the theta dt for that same triangle. I guess this wasn't too bad of a problem. I thought it would be a little trickier. We want to know how fast the rate of change is on the angle. So one thing we can do, we can use the sine function. We know that sine of theta is equal to the height over the distance. And we're going to have to go ahead and take a derivative of this here. The derivative of sine is cosine theta d theta dt. And we're going to need to use the quotient rule. So derivative of y is dy dt times d minus y dd dt, all divided by d squared. And okay, so I guess I can go ahead and start plugging in numbers, but before I do that, what is the cosine of theta? We do know that at that instant of time, y is going to be 3,000, and the distance between the camera and the rocket is 5,000. So I'm just going to write that as 3 over 5 because the zeros are going to cancel out, you know. And if we take the inverse sine, well, cosine theta is going to be 4 over 5. So let's put it that way because they're complementary angles. So easy. We didn't even need to use our calculators for that one. That's great. So 4/5 d theta dt is equal to dy dt, which we already know is 600 feet per second, times the distance of 5,000, minus y, which is the height, 3,000, times the dt, which we already found it was 360, divided by d squared. D is 5,000 squared. And I'm going to go ahead and plug in 600 times 5,000. This one, I guess I kind of need my calculator. Minus 300 times 3,000 times 360. Divided by 5,000 squared. That gives me 0.0768 times 5. Divided by 4. So that means that d theta dt is equal to 0.096 radians. Very, very little. Well, it is pretty far, so if it's that far, you don't really need to move your camera so crazily. But I am going to double check this one in the back of the book. Number 37 here of this book. And section 3. Okay. Yeah, that's right. 0.096 radians. So we are right. Very nice problem, eh? Nice problem. Should we do another problem? It's 11 p.m. Do we have time for another problem? I wish I had more time, but I do have a job to get to tomorrow morning. There's some linear approximations that I could do. Maybe next time, guys. I think I'll end it right here. Thanks for coming by, guys. Thanks for checking out the video stream. Oh, I'm sorry, 8-bit. I started a little too late. I was really hoping to stream a little bit longer. My goal is to go through all of calculus, including the multivariable stuff. Maybe even jump over to linear algebra. Maybe do some differential equations, some physics. That'd be real fun. Thanks, 8-bit. You too. Take care, everyone watching, and I'll see you guys next time. Bye!